It is my great pleasure and honor to welcome Professor Lisa Kaltenegger for a book talk appearance here at Mann on the first day after her new book went on sale. For those of you who do not yet know Professor Kaltenegger's work, she's an award-winning astrophysicist and astrobiologist, founding director of the Carl Sagan Institute, and associate professor in astronomy at Cornell University. Lisa Kaltenegger is a pioneer and world-leading expert in modeling habitable worlds and their light fingerprint, and has spent the last decade finding new ways to spot life in the cosmos, working with NASA and ESA from Austria to the Netherlands, Harvard, Germany, and now Cornell. Professor Kaltenegger is the author of more than 100 peer-reviewed publications. Among her international awards are the Invited Discourse Lecture at the IAU General Assembly in Hawaii, the Heinz Meyer-Leibniz Prize for Physics of Germany, the Doppler Prize for Innovation in Science of Austria, and the Barry Jones Inauguration Award of the Royal Astrobiology Society and Open University in Britain. Her 2017 review on how to characterize habitable worlds and signs of life was selected by annual reviews as part of a collection celebrating pioneering women scientists. Lisa Kaltenegger was named one of America's Young Innovators by Smithsonian Magazine, an innovator to watch by Time Magazine, and stars in the IMAX 3D movie, The Search for Life in Space. She speaks at events around the globe, including the Aspen Ideals Festival, TED Youth, World Science Festival, Falling Walls, and Starmus. Lisa can be found in the office once occupied by Carl Sagan, and when she is not trying to find life in the cosmos or spending alone time on her asteroid 7734, she loves reading, traveling, cooking, dancing, and spending time with friends while drinking too much coffee and Earl Grey tea. Lisa is back on Earth with us today, so please join me in welcoming Professor Kaltenegger for a riveting talk on alien Earths, the new science of planet hunting in the cosmos. Woo!
Thank you, Henrik. Thanks a lot. And thanks everybody for coming out. And everybody online for joining us. It's my real pleasure to be here at Mann Library. Like, I love libraries, I love books. And it's kind of crazy that now, there's one spot in a library where maybe my book will actually go and some other people might be able to find it. So that is really an incredible journey. But why I wrote this book is because we live in an incredible era of discovery. We found more than 5,500 worlds that circle not our sun, but other stars. And so we're at the verge now, and this is why the book came out now, because I wanted to share this excitement, this realization, and what kind of time we live. Right now we have the James Webb Space Telescope that just launched a little more than a year ago. And it is about 4 times my size in space, and for the first time big enough to collect the light from small rocky worlds and figure out what their atmosphere is made out of and whether there are signs that you can only explain with life on other worlds. So the paradigm shift has started, right? So we, for the first time, have an instrument who can do this at the edge of technical possibility. Let me add this. This is not easy. This is super hard. But to not miss signs of life in the universe, we need a lot of creativity, a lot of people from different fields working together, and a lot of ideas that we can test now with the data we get from this big space telescope. And this is a little bit of the journey that I want to take you on today. And it's going to be a little bit less than half an hour, and then any questions you have, I'm more than happy to answer. And if you have a book that you want me to sign, please let me know. And if not, if you're on campus, as Hendrik was saying, I'm in the old office of Carl Sagan, so you get 2 for 1. You get your book signed and you get to see the view that Carl Sagan would have seen. Well, with that, let me dive in and look at this. You can actually have the nebula and parts where there's stars and planets forming right now in your coffee cup. I got inspired because Neil deGrasse Tyson has one with a galaxy. And so I was like, ooh, but I want one where planets and stars form when there could be life, you know? So I have nebula. Neil has a beautiful galaxy. So I think next time we're going to toast with a coffee cup in the morning and see where it goes. But let me just position you. What is our place in the cosmos? So if you have a look at our galaxy, the Milky Way, it's about 100,000 light years across from one side to the other. And what that means is that light from one side of the galaxy means about 100,000 light years to the other side. So if you were on a planet on one side of the galaxy, you would see a planet on the other side of the galaxy like it was 100,000 years ago. And so if you're wondering, you know, ooh, why isn't everybody here? Because we have rockets, we have things, we're really interesting. We'll talk about how interesting we might be or not. It depends how far away. There's other places that looks at you too, because, you know, if you're far enough away, you will see dinosaurs walking on our own planet. And we'll talk about this a little bit, how alien dinosaurs are actually easier to spot. It's actually not true. But the time when dinosaurs lived and we had more oxygen in the atmosphere that allowed for bigger creatures to roam this planet is actually a time where this light fingerprint that we're going to talk about of a world would be a little bit easier to spot. And so you are here about 28,000 light years from the center of our galaxy where there's a black hole inside. You don't see the black hole because there's so many stars moving around it that you just see a really bright spot in the center of our galaxy. But you were roughly here 28,000 light years from the center, and our galaxy has about 200 billions of stars. And we'll get back to that number. That's just huge. So we have an inventory of our place here. So this is our sun. Then we have the 4 rocky planets, and then we have the 4 gas giants in our planet, in our solar system. And the interesting thing is that the time that light needs to get from one planet, from the sun to one planet to the other. And so Peyton Stark, who's the artist who made all the graphics, original graphics for this book, did an amazing, amazing job to take the science and make it visual. And she was like, ooh, we should do like old sci-fi style. So all these animations or all these pictures in the movie are a little bit old sci-fi style. But all the inclinations of the planets are right. All the 4 gas planets have rings because they all have rings. And all the positioning is correct, but the distance between them here is not, because we would have to have a much, much, much bigger graph to get this on. But so even from the sun to us, it's 8 light minutes. And the way that I explain this in class is like, if the sun were to explode right now, I wouldn't know for another 8 minutes. So I would be happily living for another 8 minutes before I figured out that the sun has exploded. And then you're going to say, don't worry about it. There's no reason to think that the sun will explode because we have learned about stars and that they live for billions of years. But light has a speed limit. So that means everything that you see tonight on the sky has already happened, but the information gets to us right now. And so sometimes that's really frustrating where you think, oh, light has a speed limit, so I want to know what's going on here in the galaxy. But because light has a speed limit, actually around us time goes further and further back the further away we look. So basically when we look at far away regions of the galaxy and then further to other galaxies, we always see these regions further and further back in time. So because light has a speed limit that might be frustrating sometimes, we get to see and unravel the start of our cosmos, of our universe, What is pretty amazing, because the Earth wasn't around for the first 2/3 of the history of the universe, but we can actually see what it was like because of that speed limit. So it's a plus and minus, really. And in case you're wondering how fast light is, 6 trillion miles per year. It's really fast. From us to the moon, about a second. From us to the sun, about 8 minutes. From us to the next star over, about 4 years. That's some of the distances. And so if you want to think about it differently, if you take the sun and the 8 planets around it, then shrink that to the size of a cookie. And usually I say in my class, now every time you eat a cookie, you have to remember astronomy in my class. What is a thing everybody loves, of course. And then the next star in the same scale is about 4 football fields away. So, trivia night, if you watch a sporting event, you can just bring in the distance in the galaxy right now. That's also why I wrote this book. There are some things that might actually be like, just, smooth into a conversation if you wanted to go a different way. So science is this incredible fabric of knowledge that spans through time. And when you hear at Cornell, we just went with my class to the amazing rare manuscript library that we have here on campus. And Henrik was very kind, Henrik and Laurent, to actually show us the incredible books we have here at Cornell at the rare manuscript library to see, for example, this is Galileo's book. And so this is Laurent showing us all these books, like that hold this knowledge that now, after all these years, allow us to actually go and find alien Earth. We don't know if they're alien Earth, right? We know that they're planets, we know that they're rocky, and we know that they're at the right distance, not too hot, not too close to the star, and not too far away. But the question becomes, how are we doing this? And why is it so hard? So when you think about the size, a star is big and bright, and a planet is small and not bright. So if you put the Earth 100 times next to each other, roughly, that's the diameter of the sun. And I brought a NASA picture of our own sun here because you see that even the eruption on the surface of the sun, so a sun is a huge ball of gas, it's super hot, even those eruptions are much, much bigger than our own planet. Here's the Earth to scale. The good news is we are not there. That'd be a really unhealthy place to be. But for size comparison, we're trying to find something very small next to something very big and bright that actually varies in brightness. So that's the level of how tricky this is. And so the way we actually do is we're finding new worlds not by spotting those planets, there's only a handful that we spotted, but by actually looking at what they do to the host star. And so what you see here is that when a planet goes around the star, it actually tugs gravitationally on the star as well. And so the star basically moves because the planet tugs. So if I can read the light of the star, I can see its movement. And so this is shown here because if a star goes away from you, then the light is redshifted. If it goes towards you, it's blue shifted. And you see a wobble, red shifted, blue shifted, red shifted, blue shifted. You know there's something going around that makes the star move around the center of mass of the system. And in case you were wondering how we know that the universe is expanding and that it had a start in a Big Bang, because on average, all the galaxies we see around us are redshifted. They're moving away from us. And so you can use that speed to figure out what was happening in the past and when everything was so close together that it was just in one point. And this is how we determine the age of the universe, 13.7 billion years, and that there must have been what we call this Big Bang, this explosion of space and time. And so reading the light of objects on the sky is unraveling secrets in the universe, not just other planets, but also how the universe began and gives us some ideas of how it might end. And so the first planet around a sun-like star was found like this with this wobble technique because it moved. But most of the planets now we actually find because if by chance the planet goes in front of the hot stellar surface from our point of view, what happens is that the star appears ever so less bright for a little time. When the Earth does this, it's once a year for 12.8 hours. So you have to keep spotting this. You have to keep looking at the star not to miss it. And this is what you see here. So if by chance, and it doesn't happen often, it's less than a 10% chance, depends on the distance of the planet from the star, you see the brightness of the star dip ever so slightly. It's not even a percent. And we see that frequently. So we can actually figure out that something keeps moving around this other star. And going back to science spanning all the ages, Kepler figured out that how long a planet needs to go around a star actually is connected to how far away it is. The further away a planet is from its star, the longer it needs to go around it. So if you can figure out how long it takes for a planet to go around, you can figure out how far away from the star it is and how hot it is there, roughly. And this is how we're focusing in on these planets that are at the right distance, not too hot and not too cold, in what we call the habitable zone. So there could be liquid water on the surface of the planet. But one of the things that I love about this field is that there are thousands of new worlds we've discovered. I said more than 5,609 today. It's gonna go up. We have more than 10,000 candidates that will get added to this pile. And we start to see pattern. We start to see planets that we couldn't even imagine, planets that even sci-fi didn't imagine. So the planets we're finding are weirder than some of the weirdest sci-fi worlds you could imagine. What is kind of cool, because I think that now Hollywood and writers actually have to catch up to what science is finding. But one thing that's really interesting here is that with everything we found, we figured out that 1 out of 5 stars has a planet in this right distance, not too hot, not too cold, and small enough that it could potentially be a planet like ours. As I said, we don't know if it is, but we have for the first time the tools to now investigate, to figure out if location and size then will lead automatically to a planet like ours, or in only very few cases. And so the bulk of the book is about how we're doing it and what we have to know to do this right. But 1 out of 5, remember I told you 200 billion stars in the galaxy, in our galaxy, the Milky Way alone. So 1 out of 5, and of course, we at Cornell, I'm sorry, billions and billions of possibility. Because we do have a legacy here that we should uphold, whether or not he said it. In the end, he said it in one of the interviews as billions. But we have billions of opportunity. And that's what's so exciting. Billions of opportunities, possibilities out there, and now for the first time a telescope that can take the first step at getting us the answer. And so this is another original drawing that Peyton Stark made. And what I found fascinating, I don't know if you've seen that, this is our British cover. So Penguin Press picked this cover, and the US picked this cover. And so it's really interesting because they got the same book. And in case you don't know, an author is not responsible for the cover, but you get to veto it. But they were like, I got this one first, and I'm like, oh, this looks really great, right? Because this is a region where planets and stars form, and so it makes a lot of sense. And then I got this one. I was like, oh, this one is also really great, right? But it's kind of, it's really surprising if you think it's the same book. It's the same book. The people read it, and one team came up with this is the best cover to actually show what it's about. And one team came up, this is the best cover. So I got the best of both worlds because I get both covers. And you know, they would probably want me to say, you should get both options. But what's just beautiful is in this adventure story of our cosmos, on this evolution story of our cosmos. And this is another graph that Peyton made. It's beautiful, and it's actually accurate, even so it's nice and cute. But we had the Big Bang, and then there were the dark ages before the first stars and galaxies formed. And then you see that, the galaxies form, a couple of stars that I would call out in the book formed, and then the solar system formed about 4.6 billion years ago in its 13.7 billion stories. So the Earth and the Sun, our system, missed 2/3 of the age of the cosmos so far. And then you have the big impact, so the moon gets formed, the first single cellular life starts, and then in the last part, that's actually really a tiny fraction of the story of Earth even. You have the evolution of multicellular life because there's oxygen and a high energy resource now that life can use to become more complex. And then you have the Cambrian explosion, you have dinosaurs walking around, the Himalayas start to form, Homo sapiens, and the space age and radio signals. So the story is a fascinating, fast-pacing story. Let's see where it goes. But I was saying every fifth star might be another Earth. But how can we tell? Because that's really what we want to figure out. How could we tell? And so remember when I said that astronomers get most or all of their information from light? Signs of life are written in the light of a planet, if you know how to read it. And that's what we do it. But one of the things that I want you to take from this is that we're not just looking for a carbon copy of our own planet. Green plants, oceans, all of that would be great. But even if you just go at our beautiful world, you see colors, very different colors that life uses. And it's biopigments that actually help you survive in different environments. And I'll show you a couple in a minute. But this is why here at Cornell, I built the interdisciplinary Carl Sagan Institute with a lot of my amazing colleagues from many, many different fields to tackle this question. Because I don't think an astronomer can do this alone. I don't think a chemist can do this alone. I don't think a biologist can do this alone. Everybody's amazing, but together, you need to put the puzzle pieces together to not miss signs of life if they're out there. And so the Carl Sagan Institute, built on the legacy of Carl Sagan here, is the place where we come together. There's always coffee and there's always sugar. So whether it's like cookies or chocolate, it's in the space science department, and we have a coffee once a month where ideas fly, and a lot of good espresso is served. So in case you're interested and you want to know where the best coffee on campus is, talk to me. And so we have more than 40 researchers from more than 15 departments working together on this question, trying to figure out how we could find life in the universe. And so I'm talking really about the faculty involved and the senior researchers. So I just wanted to bring in a picture of my team. This is my team. I don't do this alone. This is me. All these people are helping, trying to figure out how we can find life in the universe. It takes a village, it takes a planet, it takes an international collaboration, lots of ideas to do this. But we are en route to do this. And so when you take Voyager 1, Carl Sagan was the person who led the team that put the golden record together. Voyager 1 took off. It explored unexplored areas of the outer solar system. It saw moons for the first time. It found geysers for the first time. It found so many incredibly science things. But before it got a gravitational kick to be pushed out on its path towards the next star, it has not left our solar system yet. Our solar system is very big. So it's going to take about another 10,000 years before Voyager 1 or Voyager 2 will leave our solar system. But it has left the protective bubble that the sun creates. And so it is in interstellar space. But in case you're wondering about all this news, it's like, Voyager 1 has left the solar system. Oh, no, it didn't. Oh, yes, it did. Astronomers still insist that it hasn't left. 10,000 years of this is probably going to be what we have in the future, and then it will leave the gravitational pull. But most of the instruments were turned off because, once you go out, you want to preserve as much power as you can to get information back. And so Carl Sagan petitioned NASA for a long time. He said, like, you have to look back. You have to give us this image of our home planet from so far away. And this is what you see here on the right. This is the image of our pale blue dot. This is the Earth seen from a distance a little bit further out than Saturn. And that's it. And Carl Sagan has this beautiful poem about it, like a mote of dust suspended in a sunbeam. And so this is us, and we're trying to figure out what this world is like. And this image was taken 30 minutes before all the cameras was turned off. It was that close. A last look home before the instruments got turned off, and it went into the cold, lonely vastness of space. Or it went to become a messenger and an explorer, one of the first humankind has sent out. So if you see a planet like this, how would you know? Going back to the question, how can we spot life? And so what you want to see is oceans, mountains, green vegetation, whatever you can do. But we won't get enough light. Even with the biggest telescopes we're building right now, with the biggest telescope we're envisioning, remember the cookie scale? We're trying to make that picture now not in the cookie, but 4 football fields away or more around another star. So the way that astronomers do this always is actually everything that makes the planet will leave a sign in the light fingerprint of the planet. And so what we do, instead of actually saying north, south, east, west, because we don't have enough light, is we split this by color. We split it by energy. And you can think about this as on the right here being blue light and on the left being red light, just like a rainbow. The white color is basically split into all its different color components. Here I'm showing you the infrared, but it's pretty much the same. It's just a different range of light. And what you see here is that this is not smooth. What it should be is actually a nice smooth curve. But you see that some energy is missing because what I plot here is energy versus color. And so the energy is missing tells you which molecules light hit before it arrived at my telescope. Because remember, molecules have a different structure. Like if you have a water molecule, 2 hydrogen atoms, 1 oxygen, if you hit it with just the right energy, it will start to rotate and swing. An oxygen molecule, 2 O's, has a different structure. So you need a different energy to make it swing and rotate. But when it does, part of that energy doesn't get to me, doesn't get to my telescope. And I can do that in the lab. I can fill like a see-through canister with water vapor, shine the light through from one side, and figure out what doesn't come through on the other side. And then I go and I compare, and this is what you see here on the bottom. So you basically see, and I'm not supposed to go too far away from the mic, what you basically see is there is light missing. And I go to the lower bottom here, and I say, okay, if it's missing here at around 15 microns, that's where CO2 actually swings and rotates. And so I can read the light fingerprint, and I can read the composition of the atmosphere by comparing the missing light. A little bit like a passport stamp. In a passport stamp and a passport that tells you what molecules that light encountered before it got to us. And this is how we can explore planets far away. And the bad news is that this is the Earth. We haven't found another planet where we can do this yet. This is really hard to do. We're working on it, but we know what the Earth would look like. And that's the light fingerprint or the golden fingerprint we look for. Oxygen with a reducing gas like methane, because oxygen with methane reacts to CO2 and water very fast. So if you see it at the same time, it has to be produced in big amounts. And for oxygen, we only have the explanation that this is life under some caveats. The planet is not allowed to be too hot. You're not allowed to have too much CO2. But with the context, we can identify signs of life in the light of a planet. And so as a last point that I wanted to make here is there is an incredible amount of different kinds of life here on the Earth. And Peyton did an amazing job, and we called them alien wannabes. Because basically I was just Googling. I was Googling like the weirdest life forms on Earth, right? And I came pretty much to the deepest part of the ocean, and it's incredible what kind of life we have here on our own planet. Man, if you would give it to me, I'd be like, oh yeah, if you tell me this is an alien you got from somewhere, I'm like, yeah, I believe you, right? It's just like, there's weird and amazing and bizarre and great life. And some of it, like the tardigrade here on the top right, you can cook, you can freeze, and it can go into what's called a tune state. So it can dry out and shrivel up, and then it can survive pretty much everything. And we know that because the European Space Agency researchers decided to send them to space, wait for it, on the outside of the rocket. And then they brought them back. This experiment was called TARDIS, just in case there are any Doctor Who fans here. They brought them back. They dribbled some water on them because then they go out of their tune state. And 50% of them were fine. They were like, da 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 da, lay an egg, be happy, right? So it is incredibly what life can do here. And just as a tip, in case you ever meet an astronaut, who are incredible people per se, like every astronaut I met is super nice and super kind. But I gave a talk and a meeting of astronauts about this. And I was like, and this is the perfect astronaut. Silence. The whole room was like, I was like, but it can't drive a Mars rover. So we do need other people. So, but it's incredible what life can do and what life can survive. Because perfect astronaut, you don't have to feed it. You don't have life support. Once you get to Mars, you put a couple of drops back on it and it's going to be fine. But communication is going to be really, really hard. And we talk about that in the book too. But life on the Earth has this beautiful diversity and this beautiful palette of colors. And so one of the other things we do here at the Carl Sagan Institute is generate a color catalog of life. And this is what I do with my microbiology colleagues here. And so one of the things we're doing is we're trying to create a database for biopigments, for reflectivity of life. And that is, again, to not miss signs of life if they're just a little bit different than the green vegetation we have here. And so I take you in the lab, and if you happen to have seen the Cornell Chronicle recently, so our newest paper led by Lidia Coelho, who's here in the audience, who actually grew all of this, is about purple might be the new green, because purple bacteria has so much more versatility. It can live in so much more kind of environments. And Earth might have been purple at one point. Just saying. The things we learn about our own planet by trying to find life somewhere else is pretty astonishing too. And the last point I did want to make is when you do this and when you're trying to find other planets with life out there, you start to wonder, actually, where could we be the aliens, right? If you just had our level of technology, I'm not asking for much, sorry. I hope I'm not asking for much. Our level of technology, you can't even travel to the next star, but you have a telescope like the James Webb Space Telescope, or maybe one a little bit bigger, like the Habitable World Observer that we're designing right now. Where would we be the aliens? And you can actually figure out which stars would have just the right position to see the Earth go in front of our sun from their point of view and read what's in our air. And this combination of oxygen and methane that I talked about, that's been around on the Earth for about 2 billion years, because our biosphere changed our planet and is changing our planet significantly. And so for about 2 billion years, there is about 2,000 other star systems within 300 light years that could have spotted us. And so it was pretty funny, the news that went around the globe when we published this result a couple of years back. And one of them that I like was like, are you feeling watched? Remember, dot of light, very far away. You don't see the planet most of the time. So it's not that you have to worry about being watched in terms of what you have in your coffee cup in the morning, right? Planets or galaxies or coffee or tea. But what's incredible is that we have the technology for the first time ever. And being here at Cornell and having established the Carl Sagan Institute with some of my most amazing colleagues and open to whoever is interested in actually joining us, I wanted to stop this presentation with just the greetings that I was talking a lot about Voyager 1, the greetings we sent out to the cosmos. But what's different now, Voyager 1 launched in 1977, and Carl Sagan here at Cornell actually put together our message to other potential music lovers out there in music and in images and in greetings. What is different now is that we have evolved to the stage where we can look, where it doesn't matter if somebody else wants to communicate. We can look for signs of life that a hemisphere or that a biosphere leaves in the gases of an Earth. But it's kind of interesting to come back to the Voyager record, to come back to the Golden Record, and think about what we might want to do different or what we might want to put on a record now. I don't have an answer for that because that's a question for everyone. What would we want to say? But I want to leave you with what we did say on the Golden Record.
Hello from the children of planet Earth.
Of the government and the people of Canada to the extraterrestrial inhabitants of space.
Paz e felicidade a todos. Bonjour tout le monde.
Shalom, hola y saludos a todos.
Hartelijke groeten aan iedereen.
Are we alone in the universe?
And with that, if you have any questions, except for this one, I can't answer yet, please ask away, and thank you so much for coming out today.
So if anybody has a question, please wait for the microphone to come to your seat. Just raise your hand and Evelyn will come over.
We have about 70 people joining us on chat. And so I had a question here from Niels that says, what telescope or other instrument do you wish you had to further your research?
Oh, I have a big wish list. The bigger the telescope, the more light we can catch. The more light we can catch, the more details we can see. So my wish list is like for Christmas, the biggest telescope possibly that I could wish for. And then I would also love to have one in the visible where our eyes see and one in the infrared where we see heat. Because in astronomy, we learn so much currently with the James Webb Space Telescope and Hubble because we have different ways of seeing the same thing, the same object. And so that's what I would wish for. Big telescopes that give me the range of information from what the planet reflects to how hot it is, what molecules are absorbing, what atoms are in the air. And then if you go to the visible light, this is also where when you hit the planet and the light gets reflected out, this is where you can see biopigments. And the idea behind that is Carl Sagan said, extraordinary claims require extraordinary evidence. And I think they do. You know, just calling this is life is easy to do if you don't have to back it up. But if you had this gas mixture that I cannot explain with anything else but life, right? That is great and interesting. But if I had this gas mixture and I had the reflection from a biopigment as I know it here on Earth, this is such a stronger two-line of independent evidence. So as I get a wish list, I want 2 big telescopes at different wavelengths, big enough to collect enough light from those planets, and I want it for exoplanets only. So no sharing with this black holes and galaxies and the beginning of the universe kind of thing that some people seem to be interested in. What is, of course, absolutely great that there's so many secrets of the universe we're uncovering.
Excellent talk. Excellent presentation. I have a question which is relevant to previous one. Which types of planets can you observe and more interesting to observe with James Webb Telescope? Is it only massive planets or intermediate mass or smallest?
So the big difference, thank you for that question, is that the James Webb Space Telescope is for the first time big enough so we can do these rocky worlds in the habitable zone around red suns. So 8 out of 10 stars out there are actually not yellow like ours, but they're small and red. That's really great for us because a smaller star means less light from that star that I have to overcome to see that planet. So luckily, nature seems to make a lot of rocky planets around these small stars, what's great for us. So anytime you hear about a potentially habitable world that we either discovered or that we actually investigating, it has a red sun in its sky. Because this is where we can find it, because it's so hard to find. Remember, the sun 100 times next to each other is the Earth is the diameter of the sun. If you make it a small red star, you get to about 10 to 15 times next to each other. So just the planet being the same size as Earth is just a bigger signal. And we take bigger signals if we can get it. And so then what you want to do is you want to actually have a look at the air of that planet. And if you shrink a planet to the size of an apple, now what we're trying to do is we're trying to analyze the air on that planet that's like thinner than the peel of an apple in that comparison. So the signal is getting smaller, 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 smaller. And so back to your question, it's the first time that we can do this for Earth-sized planets at the right distance around the smallest red stars. The smaller the star, the better. The closer to us that star is, the better, because light goes out in a sphere. So we lose light the further away we are. It appears less bright. And so what we're doing right now is we're observing the TRAPPIST-1 system, the system of 7 Earth-sized planets next to the star. And what's really interesting there is that 3 of them are within the habitable zone, and some of them are too hot, and one of them that we know of is too cold. So in a way, if I get back to my wish list, is if I could wish for a system, I'd be like, ooh, what happens to an Earth if it's closer to the sun and then like further away from the sun, right? And yeah, I'll take 7. And so that is the one system where all the astronomers who are trying to characterize rocky worlds are throwing all their time in, all the time we can get at the James Webb Space Telescope to get information on this one system, because it's really hard to get and we have to add the information up. So it's going to take probably a couple more years, but for the first time ever possible to do this and do the small planets. And we do the big ones too. A lot of great people, even here, a lot of great people all over the world and at Cornell are doing this for the big planets. And for the big planets, it's great. You might have heard some of the James Webb Space Telescope announcements, right? They're like, oh, we found CO2 in the atmosphere in one transit. And you see a line, it's like, and you're like, oh, because it's such a big telescope. It gets enough light from these big, massive planets, but it gets just enough light from the small, rocky worlds too, that with time and patience, we can do the same thing for the small, rocky worlds. And we're designing bigger telescopes, right? So my wish list, we're designing things like the Habitable World Observatory or the LIFE mission in Europe. So it's basically 2 different wavelengths, big telescopes, to try to do this exclusively for planets in the habitable zone around other stars.
So we have a lot of questions, and I want to say we probably can't get to all of them, but let's see. Mark says, thanks for a lovely talk. What is the Earth size range of exoplanets with potential life?
That's a great question, and one that we didn't know much about. And so there are some of the planets where we actually have both. We have the wobble of the star, and we have the planet go in front of the star so we know how big the planet is. If we have both, the wobble of the star tells you how massive the planet is that actually pulls on the star, And the way that I describe this in class, so sorry if you've been in my class, is if there's a dog that actually pulls when you go in a park and you walk, right? And the person doesn't want to go the same direction as the dog, it will lean back. And you don't need to see the dog to know that something is pulling. And so the more massive that dog to stabilize the system, the more the owner will have to actually lean back. And so we get the mass that way. And if the planet also blocks our sight, so when the star actually becomes a little less dim, we also get the radius. So we get the density. And that's exactly where this question comes from. Before we found exoplanets, we said, okay, we know what we're going to find out there. The Earth is the biggest rock, and Neptune is the smallest gas ball. So we're going to find planets between Neptune and Jupiter size, right? Smallest and biggest gas ball in our system, and rocky planets between the Earth size and Mercury. So my answer would have been the biggest Earth-sized planet is Earth size, right? But because we have the density, because we have mass and radius, we can now tell you that up to 2 Earth radii, it's a little bit less, but roughly a good number to remember, is where you can be a rock and where you are a rock from everything we know from the systems where we know both mass and radius. Above that, you actually probably need a lot of gas to make that radius work. And so anything below 2 Earth radii, I will put in the bracket of potentially Earth-like. And if it's at the right distance, where it's not too hot and too cold, then you get a gold star. And currently, we're 48 of these planets in our list. And so the first system, the TRAPPIST-1 system, is where we're looking at 3 of them, 3 for the price of 1 observation. And then hopefully we get to the other ones too.
Thanks, Lisa, for a great talk. I'm curious, as we listen to questions, what kinds of questions, you've given lots of public talks. What are the bulk of the questions? The audiences you talk to, what is it that they want to know? What are the questions you get? And then the second part of my question is, have any of those questions had any effect on the work that you do, on the things that you look for or your team looks for?
So that's a great question. I always look out for questions that actually make me think, that there might actually be something that I haven't considered. But the advantage I have is I have incredibly good friends who actually endure my talking about my work, and then they'll ask that question for me way before the audience can actually get to the questions I haven't considered. And also the Carl Sagan Institute. So I have been talking about chemistry, biology, right? I'm talking about the sciences, but that's not all of it. We have like science communication, we have performing arts, we have music. And so that kind of friendly, collegial environment actually gets those questions to you, you know, from somebody sitting next to you and it's like, have you done this? And you're like, no, somehow I've never thought about it. And that's exactly what you were pointing to, right? That these are the questions that get missed if you're not interdisciplinary, if you don't think wide enough, if you don't discuss wide enough. And so the Carl Sagan Institute is trying to catch that and do this here at Cornell. But I always, every time I go to a talk, I'm like, maybe somebody's going to ask me something that I have no idea about or something I didn't consider. And then I think I'll show you how science works by saying, I never thought about this. This is a great question. I will have to look it up or figure out how it's going. Because science is this beautiful structure that is actually flexible, that has new questions that I've never thought about. And that's why I love it. That's why I love working in science, because there's always something new and always surprising.
Lisa, there's a bit of a softball question for you. So as I've been working in the astronomy department many years, I know that bigger and bigger and bigger is better and better and better. And I think you said a couple of times you would like a bigger telescope. Can you see an exoplanet from Ithaca?
Ooh. So, if you don't mind how big the exoplanet is, if you love a gorgeous, majestic planet like Jupiter that only needs a couple of days to whiz around the star, oh yeah, you can see those, the dip of light from Ithaca, if it's clear. Currently, today, we're going to have trouble, but yes. And this is also, I think, where it becomes so approachable and textile, because you can actually do this with small telescopes. For the biggest stars, that whiz around their star. These planets that the biggest planets that whiz around their star, these planets we hadn't imagined. I didn't tell you this, but the first planet they found, they built the instrument who would be able to do the wobble of the star. They knew they couldn't do anything smaller than Jupiter. So they set in to wait for a decade, right? Because Jupiter needs 11 years, but more, nearly 12, to go around a star. So astronomers are patient, not just space astronomers, also people on the ground. And they found a signal in 4.5 days. So Monday morning to Friday afternoon, and the year's over on that planet. And that was one of the biggest surprises just right off the bat. And that's the Nobel Prize that they got for exoplanets. But so they had a big Jupiter-like world. It cannot form where we found it because it wouldn't have enough material. And so this spiraled into what I love about exoplanets. We find something, and then we have to try to explain it. Because there are so many great surprises, because we just had a sample of one, our own system, and now with every other world that we find, some worlds actually circle the stellar corpse of an exploded star. This is just before 2020 when we found it, and that was the test mission, and I was on it. It was like really great. We're like, so really? The star exploded and the planet's still there? How would that at all work, right? But it is there. And exoplanets are observation driven. So if that white dwarf, the stellar corpse, were actually closer, that would be a whooping signal because the planet is actually bigger than the white dwarf. What's like crazy? And so then you would see, now you see the white dwarf, no you don't. Now you see it, no you don't. This is also why we didn't find it for the longest time, because our pipelines, the methods that we have to find planets, we're not expecting whooping signals. We were going for less than 1% because that's what we knew. So you can see it from Ithaca on a beautiful sunny day or on a beautiful cloudless night. And I think that's also really great because, again, this connection to the universe that we all share is there by seeing another world circling its sun.
On here we have Jorge wonders, will AI speed up the discovery of new life on other planets?
Absolutely. So what AI does really good, but in my point of view, what AI does best is pattern recognition. And pattern recognition is really, really important because pattern recognition lets you spot things that your eyes do not spot easily. Like, for example, the reflectivity of different surfaces mooshed together on another world where you only see a dot of light. AI is really good at actually decomposing that signal and saying, oh, there's X amount of green and snow and sand. So we've written some papers on that. But I think where I see a huge impact of AI for science in general is that if you use it well, you actually can curate information in a moment. Where you had to go and read all these papers and find them and figure out what you should read, now you have a tool that will scour all these archives for you when you say, now, take the whole Mann Library, everything that's online, and figure out which sources there are that mention exoplanets. And then I now need this information for them. And it will actually tell you all the sources you need to consider. And that's not just for exoplanets, but generally for any science and also, social sciences or for any literature search you have or anything that will just cut the time. And if you can cut the time and let people actually think about the results and analyze them, this is where I see this great power of AI. Of course, we have to figure out if we use it for good or evil, but that's on us, right? Because pattern recognition also recognizes what you and I want to see, for example, on the internet, or what we'd like to get. So I think the huge power, the change that we're just going through is a little bit like we didn't have computers before, and then computers could do this calculation for us. And we have so much information currently that now we have a tool that can actually focus and scour through all that information for us. And that's what I'm very excited about.
Thank you so much, Lisa. This has been really fun. you said we're only a sample size of one. So it just makes me wonder, like, so have we absolutely determined that there's no life in our solar system outside of Earth? I mean, I'm thinking about the moons of Saturn, maybe, you know, like what's out there that's nearer to us?
A great question. Thanks for bringing this up. We haven't found life anywhere else yet. The yet's really important, right? But what's really, really interesting is like when we think about the places where we search for life here in the solar system, those biospheres, as far as we know, do not change the overall appearance of the moons or the planets, right? There's no unique sign. Like if Mars had like a completely yellow mat that would cover it, that's biota, right? Then that's something I could see on a planet around another star. But if I have to go subsurface, whether it's like, you know, under an ice layer in an ocean, this is why we actually go there, why we sample, whether it's Mars or Titan, Europa, and Enceladus, right? Where we actually have to drill through the ice, where we have to take samples from subsurface to analyze. So the search for life in our solar system is absolutely fundamental to try to figure out what else life could do on other worlds, what other gases it could potentially produce. But for now, we don't know any of that yet. So we're building our search for life as we know it, our own Earth. And there, what I try to bring out in the book too is that the Earth, if you had a time machine, what doesn't work to go back in time with Einstein, right, does not work. But if you had one, if you had the TARDIS, and you would go back in time, you would not be able to identify our planet as our planet because our planet has changed so incredibly significantly since it was born. And also for the first 2 billion years, there was no oxygen. So bring a gas mask or you open the time machine and you're dead. Not a good choice. But the interesting thing is if you go at different stages of Earth's evolution, you would actually see it as kind of an alien planet, a very different kind of worlds. And so even though we have only the sample of one, we have the sample of one through time. And so that brings it out not just by the diversity of life, but also by the age and evolutionary states into a couple of samples that we can use as a template to try to find life somewhere else. But the huge difference is that to do it around another star, the biosphere has to change the whole planet like it did on Earth. If it doesn't, if there are worlds where the biosphere would not do that, then we're blind to life on planets around other stars. But again, sample of one, it did here. So chances are it should do somewhere else too that we can spot.
I have a good follow-up question for that. A couple of weeks ago, the Cherry Theatre, local theatre, had a play called Carbon, and that sort of explored what would happen if alien life was not carbon-based, because as we know, life is carbon-based. So when you are looking at methane, for example, you are looking at life similar or at least carbon-based. Is there a conversation among astrobiologists about non-carbon-based life, or is that just going to remain science fiction?
Absolutely. That conversation is also really important because you don't want to just figure out that, oh, you look at this niche environment, right? Carbon and water might not be what life should usually use, right? But when you look at it in detail, then you see that you need something that can make complex structures. But what a lot of times we don't think about so much is that you also have to be able to break those structures to recycle. And so if you take carbon, that's really easy to do. You don't need much energy to actually break those complex DNA, RNA structures again. But if you use, for example, silicate, then you can make these complex structures, and you basically look at elements that are similar in the periodic table, right? Because they should have similar kind of properties and could make like cells and things. But the problem is actually breaking these other structures requires a lot of energy. So it might be energetically way too costly to use something else. And if you thinking at a certain distance from the star where you have a solvent like water, then you would also have some oxygen. So carbon and oxygen make CO2. It's a gas that's soluble in water at the temperatures we have. Silicate and oxygen makes quartz. You need to go to 2000 degrees to get it back. And so there are some reasons why we think that carbon might be the best choice currently, like the most versatile choice. But when you look at the cosmos, you see hydrogen, oxygen, and carbon pretty much everywhere. The one key difference that will happen is that this habitable zone that I kept talking about is the liquid water zone on the surface. Titan, that we brought up before, is further out, so water has frozen. It's not warm enough. So then other solvents, like for example ethane and methane lakes on Titan, could potentially take over the function of a solvent, the function of a liquid that allows chemicals to actually regroup and make structures and make cells and make like interesting chemistry. But we haven't found that yet. And this is why the exploration in the solar system is so important, because we're actually sending a quadcopter to Titan, and it just got approved with the launch date of 2028. It's going to take a while to get there. But Dragonfly is going to go to Titan, and people here at Cornell are working on it in case you want more information. But what's really interesting is going to go and it's going to sample, and it's going to figure out if there might be a different kind of life based on a different solvent. So carbon seems to be pretty solid as a choice from everything we know. There might be something we don't. But water is temperature dependent. And so if you go further out, it has to be a liquid that stays fluid even if it's colder. If you go further in, it's probably not going to be that important insofar that I won't be able to spot it, because it would need to go subsurface to shelter from the increasing and increasing heat. And so this is where we concentrate now on the liquid water zone, the habitable zone. And then we say there's a habitable zone for methane, ethane, liquids. But we don't know if it can make life. And we don't know how that would change a planet and how to spot it. Because currently on Titan is super interesting, but we have not identified any signs that we cannot explain with geology yet. So that's what we need to be able to do this for worlds around other stars.
I have a question from Seth. It says, if we look far enough, would it technically be possible to see the Big Bang?
Oh, yes. We have that part in the book. Because if you look far enough, and you actually don't technically, you don't get to the Big Bang, but you get to the part where the universe is just like denser and denser. It becomes hotter and hotter. So the way to think about it is that there's a cosmic microwave background. If you heard about this before, it's called CMB, usually when astronomers talk about it. But at one time, when you look far enough away, you will see this incredibly bright universe. And that's a certain distance that translates in a certain time, that translates in a very young age of the universe, about 380,000 years. But what you see is like everywhere, wherever you look, you actually see this hot plasma. And so what that means is that you see, a while after the Big Bang, but in 13.7 billion years, we are not quibbling about a couple of 100,000 years. So you see the evidence of the Big Bang in that cosmic microwave background radiation. And what I found really interesting, and so in the book I described this a bit more, but what I find really interesting is like wherever you are in the universe, even if you're completely at a different place, you will get to that hot plasma bubble. And so we are not the center of the universe, right? So we're not going back to that Copernican revolution. We're not the center of the universe. But in the observable universe, whoever is looking is the center of their observable universe, because at a certain distance, they will hit this hot plasma shell that tells you about how the universe started.
So Raymond asks, how do these smaller, redder stars put out light at a steady rate? Evolution requires hundreds of millions of years. If the star's output changes too much over time, will evolution have enough time for complex life to emerge?
That's also a great question. The good thing, what's really interesting actually, You know, when somebody tells you it's better if you're not super huge, but if you're small and don't eat too much, right, you're going to live longer. Sometimes people tell you this. Rat experiment, 30%. I love food. I would like to eat. But what's really interesting is that small stars actually live a lot longer than yellow stars. So the small red stars will outlive all of the yellow suns in the sky. The yellow suns will become bigger and then they will explode because they're more massive. So in their center, there's more pressure and more heat. So what that means is that the nuclear fusion in the center goes faster. So in a way, lucky for us again, that the planets actually go around these small red stars. They have much, much more time. And so we'll have about 12 billion years. So that's pretty good. We're like 4.6 in, no panic yet. But these small red suns, they will have 100 billion years. And so what's really interesting is to think about is like, what would life do with that? Like if life were to evolve on such another star, you know, it could go so much further. However, it doesn't mean that we have to end, right? We'll just have to become space travelers. Because at one point, our sun, and that's billions of years from now, right? So 500 million of years is going to get really uncomfortable hot, and we're going to start to actually evaporate the oceans. But then our star will become bigger and bigger and bigger as all sun-like stars do. And at one point, it will actually engulf the planets, like small planets, might even engulf the Earth. But whatever happens, we're going to be way too close. It's going to be way too hot, cindery on the Earth. And so this is also why I find our exploration so important, because we could have never figured this out. But we did. By observing the stars, we figured out how a sun lives and will die. And even though we're just 4.6 billion years in the 12 billion year evolution of our star, right, we have figured out that this will happen. And so we have figured out that we should get more people into engineering and science just to make sure that we either have like a big parasol, right, that helps us shade this, or some ways the very cool space stations, please. I saw some of the sci-fi movies. I want one of those with the glass windows so I can see everything while having a cool life on a cool space station. Because our star will do this. And other stars will have a much longer lifetime than ours. So it's kind of interesting to think about what that could do to life if it's there. But for now, we haven't found any signatures of life on any world. But these small red stars are our best bet just because it's easiest to find them there.
Thank you, Lisa. We could be here for another half an hour or an hour just listening to you answering more questions from the depths of the universe, but there has to be an end to it. People need to be able to get home or get their book signed. If you have been able to obtain a copy and you want Lisa to sign it, she is going to be available right now. And may I thank Evelyn and Jenny and also Sean for making the chats and the stacks possible this and every semester.